Okay, so the instruction set is the interface between hardware and software. With the defined instruction set, a programmer is able to write a assembly language program, and of course, the programmer can write a high-level language like C, then use a compiler to translate that high-level language program into assembly language program, which then executed by the processor. There are different kinds of instruction set. You can give easily a couple of examples. Intel's x86 instruction set, ARM's instruction set, and you have also MIPS processors. These processors, they have different instruction set, which means that you cannot have a program written for one processor being executed on a different processor with a different instruction set. So the language has to be the same in order for the software programs be executed by hardware microprocessors. We talk about instruction set. It's the functional appearance to its immediate user system programmer. To define an instruction set, you will need to define upper code, which is the function of the instruction. Also, you need to define addressing modes, architected registers, floating point standards. Addressing modes, as you learned from the first microprocessor class, that it is the way that to find the operands for an instruction. That's what we call addressing modes. You can find operands from registers, from memory, and from I/O devices. Architected registers are the registers with names. For Intel x86 architecture, you have AX, EAX. For MIPS processor, you have R0, R1, etc. So those are the registers with names. Underneath the architecture or the instruction set architecture, we will need to consider how do we implement the processor, which refers to the logical structure or organization that performs the architecture. So in order to support the defined instruction set, you need to have necessary components. For example, you need to have registers, right, to support those named architected registers. You need to have functional units to perform those functions defined by opcodes. You also need to have caches if you care about the performance, because there's a speed gap between the microprocessor and the memory. Now, if we go down further, we will need to consider the realization of the chip. Basically, how do you fabricate the chip from a silicon wafer? Right? That's the chip system designer's view. At this level, we are talking about the physical structure that embodies the implementation. Now, if you want to have 2 megabytes of cache on the chip, how do you fabricate that memory cells as a part of your microprocessor? So that's the things we need to consider at the realization layer. In this layer, we deal with the gates, cells, transistors, and wires. Here's an example of Pentium IV microarchitecture. This is a fairly old chip, but we use this chip as an example to show that there are many different components inside the chip. We have at bottom we have ALU here, and we have floating point operation units. We have cache. We have TLBs. We have microcode control ROMs. We have data cache, etc. So those are the components that inside the chip, logically. And here's a picture of the Pentium III Die Photo. That shows that physically, if you are to implement these different components in the chip, how you can do it. This is one way to do it. It's not the only way, but Intel had decided to do this kind of layout because the fabrication process and because of the communication among these components. Some of the components, it's better to be adjacent to the other one. Okay, and this particular chip is the first Pentium 3. It has 9.5 million transistors. It has 5 layers of aluminum, and the dimension is 12.3 by 10.4 millimeters. And the technology is 0.25 micron, which essentially that's 255 nanometers. Okay, this slide shows the hardware, the very low layer we talk about in terms of architecture. We have to deal with machine specifics, the feature size. We go from larger ones to smaller ones. That's essentially the size of the transistors or the size of the wire. We go from 10 microns from 1971 to all the way right now we have 45 nanometers and in some cases 20 nanometers. That's the minimum size of a transistor or wire in either the X or Y dimension. We will need to consider the logic designs, how we build the gates, and we also need to consider the packaging, clock rate, and supply voltage. Especially the clock rate and supply voltage, those are the two main factors determining the power consumption of the chip. Relationships between these three aspects, we talk about the instruction set, microarchitecture, and then the physical layer, the realization. Processors having identical instruction set may be very different in organization. This is to say that even the interface between hardware and software is the same. When vendors go from newer processors, they tend to keep the same instruction set for backward compatibility because you want to keep be able to run the same program. But the internal organizations will be different, and for different purposes, for better performance, for better power consumption. So the organization of the internal components are different from chip to chip. And processors with identical instruction set and a nearly identical organization are still not nearly identical. Here's an example. You may have two processors with nearly identical instruction set and organization, but they may be implemented on a different chip with different clock frequencies, different memory subsystems. Architecture covers all these three aspects. So in this class, we will talk about the instruction set. We will talk about the microarchitecture, although we may not spend so much time talking about the physical layer, the rear side layer. Applications and requirements. This is a list of different application domains, from scientific application to commercial application to embedded application to home computing. You can see that these different application domains, they have different problems to solve. For example, scientific and numerical computing, we are talking about very large problems, weather prediction, earthquake modeling, etc. Those requires very large memory and oftentimes very high computing power because you have a lot of floating point operations. You have to be able to model very complex mathematical models. For commercial applications, mainly it deals with inventory control, payroll, e-commerce. You need, of course, integer arithmetic, and oftentimes you need high performance I/O operations. For embedded computing, people are more concerned about power, okay, and also low cost, and how quickly it can respond to interrupt. Embedded processors have gone through a very fast advance in the recent couple of years, partly because the demand from mobile and embedded computing, like your cell phone. Qualcomm and Broadcom, they keep building new processors. So even right now, your cell phone, you can easily find a processor with dual core or quad core. And with these many cores, how do you keep the power consumption low? It's not only a hardware question, but also a software question. Okay? For the hardware design, of course, there are different techniques you can use to, for example, do dynamic voltage scaling to change the voltage of the processor based on the workloads. From the software side, you can do a lot of smart control based on the workloads. You can schedule some non-critical workloads later, or let some of the tasks run slower that will also consume less power. For home computing, we're talking about multimedia, games, entertainment. Those applications need very high data bandwidth and very high performance on the graphics processing. The other aspects, well, another direction in the home computing is the sensors. You now have increasingly number of sensors in your home, from your power meters and to your refrigerators, to your healthcare devices. There are a lot of sensors going into your home. And how do you connect these sensors and make sure the information that they get from the environment can be processed and stored in an efficient way? That's also a new application requirement. For these different kinds of applications, we design different classes of computers. We have high-performance computers, for example, supercomputers, and massive parallel computers. And I should add one more thing, which is cloud computing platforms. Cloud computers are, well, as known as the warehouse-scale computing systems, consist of hundreds or even millions of processor cores in a very large facility. And these processors are not in the same single machine. So this is different from these supercomputers. These cloud computing processors, they are interconnected through high-speed interconnections, infinity band or 10 gig Ethernet. They form a massively large-scale parallel computer. You can run different workloads on these computers. For example, you can run Hadoop, which is a very promising, it's a very popular computing framework. You can write parallel programs using this Hadoop framework very easily. We will spend probably one lecture on talking about this cloud computing. For the middle tier, we have desktop machines, PCs, etc. And the other end is the low-cost embedded computers, low-end PCs, and laptops, and your smartphones. The motivation of studying computer architecture, one of them is we often want to ask the question, well, when we use computers or when we design computers, we want to know, are they fast enough? The answer is, unfortunately, you will never feel a computer is fast enough. You always have increasing need on the computing. You always will find your Windows machine will becomes much slower than the time you bought it. It's partly because you have so many junk applications on it, but also because some new applications, they do require increasingly high computing power. Okay? And you have new applications coming out. Now, social networking is very popular. Cloud computing applications are very popular. But maybe in the next a couple of years, you will have some new killer applications that will require increasingly powerful machines. The other question, or the other new requirement is, oftentimes speed is not the only goal. Okay? You can have a very powerful machine, but if that computer consumes a lot of power, and you will have incentive to have a new one. Or for a person owning hundreds of these machines, he or she has a very strong incentive to have a new one with less power consumption. So power also comes together with the heat dissipation. That's a challenge for people requiring very powerful machines. Also cost. We want to bring down the cost as much as possible. And the other thing is the reliability. How do we improve this reliability of a processor? So the answer is, number one, while we study computer architecture, the answer, number one, is requirements are always changing. Number two answer is the technology playing field is always changing. There are many different pieces in the computer system. Processor is one of them, but processor has to talk to other subsystems, for example, memory and I/O devices. For logic, the speed is kind of follows the Moore's law. So every 18 months, the transistor density doubles. So you have increasingly powerful processor. But at the same time, the memory subsystem falls behind. So there's a gap between these two. And you have to keep thinking of your design, keep improving your design to address this challenge. Designs change even if the requirements are fixed, but the requirements are not fixed. As you know, you will have new applications. You want to have a new way of programming the machines. These new requirements will make the existing design often quickly obsolete or need some improvements. Examples of changing designs. Here's a very good example, although it's a bit outdated. Cache is, in fact, not a good thing at the very beginning. In the 1970s, believe it or not, the DRAM is in fact faster than logic. So the memory access speed is faster than computing. It does not make sense to have a cache as a part of the processor, because you will not improve the performance, you actually will drag down the performance. But when the processor is faster than the memory, it makes sense that you have a smaller piece of memory on chip, so that you don't have to go to the off-chip main memory. You can get your data from the on-chip memory, the cache, then you can speed up the computing. Okay? So this changing performance will decide whether or not cache is a good idea or bad idea. Performance growth. The performance of computing system increased dramatically. there's a estimation that from the Big Bang, Big Bang is the beginning of the universe. Okay, that's essentially what this means. From the Big Bang to 2001, if you measure the computing power, okay, of course, we don't have a computer at the beginning of the universe. We had it since 1946, right? The first ENIAC, the big machine. But if you measure the computing power from 2001 to 2003, you get the same absolute increase in terms of computing power, okay, compared to the Big Bang through 2001. And from 1971 to 2001, the performance improved by over 35,000 times. Well, what if cars can improve at that rate? We can ride a car and then go to the moon in a split of a second. How do we measure the performance of a computer, a processor? Latency refers to response time, execution time. That is the minimal time to wait for a computation. Throughout this class, we will use this quite a lot, the execution time. We want to use the execution time to compare the performance of different processors using the same software. We call these software as benchmarks. Another categories of application, they care about throughput. Throughput refers to the number of tasks completed per unit time, or the bandwidth. The goal is to maximize the work done in a given interval. The relationship between latency and throughput is that if there's no overlap among tasks, which means that you have task A, task B cannot be completed until, well, let me say it again. Task B cannot be started until task A is completed, and then so on. So you only, at any given time, if you have only one task running, then the throughput is 1 over latency. It's easy to understand, right? It's the inverse of that. If there is overlap, so you imagine that you have these two tasks overlapping. Okay. If you draw it on a piece of paper, then the throughput is not equal to 1 over latency. It's going to be 1. It's going to be greater than that.
Shouldn't it be less than the reciprocal of latency, since we have, in pipeline we already begin the task, like even before the first instruction has been executed.
Right.
So we are like kind of speeding up the execution.
Right.
So in that case, like shouldn't it be like less than?
You already answered the question, because you said you increase the performance. Right. You increase the number of tasks completed per unit time. Right? So the number should be greater than 1 over latency if there's overlap. The more overlap you have, then the higher the throughput. Right? So both latency and throughput are important. It's very much depending on what kind of applications we are looking at. For example, I'm using a networking problem as an example. A router, okay? It's a network equipment that will have network cables or links connected to it. You have machines sending packets from one end to the other end through this router. The time it takes for a packet to go through the router is T. Okay? That's the delay. So you can have one packet going from the input port and then forward it out from the output port. That's the time T. If you have only one packet going through the system at any time, then the throughput is 1 over T. Of course, you want to do better than that. you want to be able to receive multiple packets, process them in parallel. In other words, they have overlap, then these packets can be forwarded out in parallel. Okay? Not exactly in parallel, but they will be pushed out of the router as soon as the link is freed. So with this overlap, you will be able to increase the number of packets processed. That's the throughput. So that's the number you see when you buy a router or switch. It tells you that's 1 gigabits per second or 10 gigabits per second. That's the throughput. Okay. To measure the performance, we use some terminologies. Here we talk about the execution time. We use execution time to compare the performance of two systems. If we say X is n times faster than Y, that means the execution time of Y, because Y is faster, so the execution time is longer. The execution time on Y divided by the execution time on X equals to n. That's when we say X is n times faster than Y. We can also say X is m% faster than Y. By that we mean the difference between these two execution time divided by the new execution time, or the execution time of X, and we do 100%, multiply with 100%, that is m. Okay, that means m% faster than Y. Okay. We will use the following example to show you how to compute speedup. And here's the what's so-called Amdahl's law. Speedup is due to some enhancement E. To show this in the picture, we have some improvements to the architecture so that the time the execution time is reduced. What we see here is time before has three segments: green, blue, and green. And time after also have three segments: okay? Green, blue, and green. What's illustrated here is that for some portion of the task, this green part in the time before, this part is reduced to this because of certain enhancement to the architecture. Okay? When we compute the speedup of this enhancement, we do execution time without the enhancement, that is before, divided by the new execution time with the enhancement. So that's the time after. Okay. So what do we expect? We expect this to be a number larger than 1.
With enhancement, execution time will be less than. I think it should be the other way around. Like,
Okay.
we always like new by old. When you're calculating how much the speed or anything has improved, we actually, it's always like new by old. So old is like without enhancement, so new should be with enhancement.
Okay.
So if you are calculating the improvement factor, so it should be like after by before.
I see your point, but think about this way. I agree with you that you want to compare the new with the old one, right? You want to see you have improvement, but what you actually compare is the speed, so-called, right? Whereas speed is the inverse of the execution time, right? So if you plug into this equation, or your equation is equivalent, right? So the old execution time is longer than the new execution time, if the enhancement is indeed an enhancement, right? You want the execution time to be smaller. That is to say, we want the speed up to be a number greater than 1. If we say the speed up is 10, that means the new execution time is going to be 1/10 of the old execution time. So that's the definition of the speed up. Now we have a question to answer. Suppose that enhancement E accelerates a fraction f is a number, of the task by a factor s, and the remainder of the task is unaffected. What is the execution time after and the speed up? Okay, let me reiterate this question. Now this is the what we have before. Okay, this time is what we have before. This time is what we have after. This question is to say that this enhancement accelerates a fraction f of the task. To give you a more concrete example, let's say this and this 3 segments here are of the same size. Okay, then we can say that this blue section here is 1/3 of the original task. Okay, so that's what this fraction is about. We say that this fraction is accelerated due to the enhancement by a factor of s. Okay, so the time that you spend in this phase is reduced by half. Okay, let's say this by a factor of 2. Okay, that's what this s means. Okay, so the factor is how many times this fraction is reduced. So with these two numbers, or two symbols, can you write down a formula for the execution time after? Once you do that, then what will be the speed up? So I'll give you a couple of minutes to work on this. So let's see here. So the execution time after is the execution time before. And the two terms here is, this is the fraction that you speed up. This S is the factor. So let's say if you reduce that section to half, then the factor is 2. So you divide it by this number.
Can you just go back to the question?
Yes. Go back to the question. So we accelerate a fraction of the task by a factor S. So that fraction is going to be fraction over S. That's the new time for that part of the workload.
Suppose, as you gave an example, if S is equal to half, so...
No, S equals 2. That means half. If I say reduce by a factor of 3, that means the new time is 1/3 of the original time. Or the original is F. Right? The rest of it is 1 minus F. So the speed up will be taking this before divided by this after. So that's the speed up. Okay, let's look at a more concrete example. We have floating point instructions which improved to run at 2 times of the speed. But only 10% of the execution time are floating point operations. What is the execution time and speed up after the improvement? Of course, you know the answer is on the same page. So from the description, we know the fraction is 0.1, that's 10%. And the speed up factor is 2. Okay? So the execution time after will be, you plug in the numbers, 1 minus 0.1 plus this 0.1 divided by 2, so you got 0.95 execution time. And the speed up is 1 over 0.95, so that is 1.053. One common practice of improving the performance of processor is to make the common case fast. For example here, all instructions require an instruction fetch. Only a fraction requires a data fetch or store. Okay, make sense, right? Only the memory operations, memory instructions will incur load store instructions from to memory. But every instruction has an instruction fetch. So the common sense, the common practice here is to optimize instruction access over data access, because everybody gonna do this instruction access. Okay? If you have the resources to optimize, you want to optimize the instruction access, because that's the common case. The other things following the same direction is the locality. We are talking about 2 different locality here. I assume you heard of these two because you said you talked about the cache architecture in the first computer architecture course. So just to recap here, we have two different kinds of localities, spatial locality and temporal locality. Spatial locality means that a program, while it's executing the instructions, it turns to access the data in the same or nearby locations. Right? That's why you have these blocks, cache blocks, right? Each time you load the whole block, because you know you're going to access the nearby pieces of data. The other locality is the temporal locality. That's looking at the time scale, that the next moment, next few cycles, you have very high probability that you will access the same data. Okay, that's the temporal locality. The third thing is the access to small memories is faster. And if you have a larger memory, you have more pins that you need to decode, and as a result, if you want to provide a storage hierarchy, you want to have the smaller memory components to the processor, to the data path. This is within the data path registers, right? You register, load the store, and you load the registers and send the values to the ALU unit, right? This is the closest storage component to the processor. Then you have the cache. This is on chip, and then you have memory, and then you have disk and tape. The more you go to the right, the larger the size, but the slower the access speed. This is a very important formula. We call it fundamental law. CPU time, or the execution time, is determined by several factors. First, we use seconds to measure the execution time. It is computed from these three terms, three elements. The first one is the instruction per program. Or the instruction count. That is to say, for this software, for this program, how many instructions it has. The second term over there is the cycles per instruction. Okay, CPU cycles. Okay, depending on the clock frequency of the processor, you have different CPU cycles, be longer or shorter depending on the frequency. Here, the CPI refers to the cycles per instruction, because the pipeline, in fact, not every instruction has the same number of cycles. The CPI here refers to the average CPI. Okay? On average, for every instruction, how many cycles you have to spend. The third term is the clock cycle time. This is determined by the frequency. Okay? The higher the frequency, the shorter the clock cycle time. Taking these three elements together, we can calculate the CPU time, or the execution time. And the calculation is just multiply these two, these three components. These three components are determined by different part of the system. Let's go from the instruction count. Instruction count, by definition, is the number of instructions of that program. Of course, it's depending on the program. If you have a more complex algorithm, then you're going to have more instructions. The second thing that's determine the instruction count is the compiler. Okay? If you write a C language program, different compilers will be able to generate assembly language programs with different number of instructions, because the compilers may have different techniques in doing the optimization, in generating the data structures, generating the code. The third element that will determine the instruction count is the instruction set architecture. For the same program, using the same compiler GCC, it will generate different number of instructions for ARM processor from the Intel processor. Okay? So these three things will determine the instruction count. For the CPI, it is determined by compiler, instruction set, and the microarchitecture. We'll know more about this, but you have to make sure you understand that this clock cycles per instruction is heavily determined by the instruction set architecture, the optimization techniques used by the compiler, and also by the underlying microarchitecture. For example, different number of pipeline stages will determine how many cycles per instruction we'll need. The clock cycle time is determined by instruction set, again, by the microarchitecture and the physical design. Okay, let's do a very simple calculation here. CPI is the average CPI. That is the total number of cycles divided by total instruction count. Okay? Because each instruction or each type of instruction takes different number of cycles. The way we calculate the average CPI is by using the CPI of a particular type of instruction multiplied with the fraction of that type. Then we do a sum on these numbers. To give you an example, we have these 4 types of instructions: ALU, load, store, branch. Out of this program, which may have 1,000,000 instructions, 43% of the instructions are ALU instructions, 21% load instructions, and 12 store instructions, and the rest 24% branch instructions. Okay? Let's assume we have such a workload. And then we know for each of these 4 types of instructions, these are the clock cycles they will need to run in order for this instruction to complete. So it takes 1 cycle for ALU and 2 cycles for all the other 3 types of instructions. Okay? So going back to this formula, CPI, that's the CPI, this percentage is this F, the fraction. So the way we calculate this average CPI is very simple. Just following that formula, we will do 43% times 1 plus this 21% times 2, and then plus this 12% times 2, and then plus this 24% times 2. Okay? And the final number, this 1.57, is the cycles per instruction. And remember, we are talking about this average CPI, so that's why you can see there's a fraction number as the result. Normally, if you talk about instruction, you cannot say a half of cycles. But since this is the average number, we do see the fraction numbers. Okay, now here example, we will need to use what we have learned so far to answer the following question. Now first, let me explain the problem. We have a RISC architecture. We have a program with the following instruction mix. Okay? we have again 4 types of instructions, and the frequencies of these instructions are in this table: 40% of ALU, 20% of load, 10% of store, and 20% of branch instructions. We also know that ALU instructions takes 1 cycle. The other 3 types of instructions take 2 cycles. What a designer wants to do is to add a register memory ALU instruction. What he wants to do is to, for this new instruction, it will have 1 operand in the register and the other operand in the memory. Okay? And this new instruction will take 2 cycles. But at the same time, because of this new instruction, it will also cause the branch instructions to increase 1 cycle. That is to say, branch instructions now takes 3 cycles to complete. The question is, what fraction of loads must be eliminated for this to pay off? Okay, there's a lot of information given here. Let's go over what we have again. The table tells us, before the change, how many instructions I have in each category, right? So the table says I have 4 types of instructions, and the frequency row tells us how many instructions of those. Right? Now the new enhancement to the architecture is this new instruction. This new instruction will have one operand in the register and 1 operand in memory. And it's gonna do the ALU instruction. Okay? Before this new instruction, ALU is ALU, load is load. This new instruction is gonna take the ALU and take the load and do all these 2 things together using 1 instruction. So if this new instruction is introduced to this design, we will expect that this frequency will be reduced, this frequency will be reduced by a certain fraction, and by the same fraction, in fact. Right? Because when you introduce this new instruction, let's say X%, it'll take X% from the ALU, take X% from the load. Make sense? Okay. This new instruction will take 2 cycles. But it will also increase the branch instruction to 3. So in a new design, this percentage is the same, 20%, but the number of cycles is increased from 2 to 3. So the question here, in fact, is what should be the X, the percentage, so that the new design will have a shorter execution time. So the way you should think to solve this is, remember the formula, the CPU time equals instruction count multiplied by the CPI multiplied with the clock cycle. Okay. So you need to think about what is the new instruction count, what is the new CPI, and what is the new clock cycle time. Then compare the before and after. So I'll give you a couple of minutes to solve this. Do you want me to go forward, or you want one more minute?
I think it is 1 by 15.
Okay. Let's see. So we have now, instead of 4 types of instructions, we now have 5. This last row here, this is the new instruction. This is what we had before. Okay. This is what we have: the frequency, we have the CPI, and we have the average CPI. When we introduce this new instruction, let's say we have X percentage. So what the effect of adding this new instruction is, we reduce the number of ALU instructions, and we also reduce the number of memory instructions. So that becomes 0.5 minus X and 0.2 minus X. This is the same. Well, this is different. You have 3 cycles, but the other ones are the same. So you can calculate the average CPI using the total number of instructions. Right? Now it's 1 minus X. This is the average CPI. Again, we come back to the execution time. We know the instruction count, multiply with the CPI, then the cycle time. What we want to find out is this X, so that the old execution time is larger than the new execution time. That's where we can get benefit. Cycle time, that's the same, as we assume there's no change. So that gives you this formula, right? So what you see here is X should be greater than 20%. 20%, that means all the load instructions have to be replaced with this new instruction in order for this formula to hold. So the math here is simple. I think more important is the changes when you go from the old design to the new design.
Reduce the store instruction.
Right, it does not. It does not.
It will access the memory.
Well, the question we give out is that this new instruction is doing the ALU. That means it's going to load operand, but the result can be still going back to the register. So it's not changing the store time. Okay, next few slides I want to quickly go over the concept of benchmarks. Benchmarks are widely used in evaluating computer processors' performance. Benchmarks are essentially programs, and they are used as unit of work. There could be millions of programs, not all the same. Most are very different. People have been using standard software programs as benchmarks to measure the performance. And these benchmarks can be in many different categories. Spec.org has a large set of standard benchmark applications. Also, there are other open source benchmark applications which are widely used in computer architecture research. Here are some examples. You can have toy benchmarks in a sense that not really useful ones. For example, quick sort, puzzle. These are used in the early days. Also, there are synthetic benchmarks which attempts to match average frequencies of operations. There are kernels which frequently used to execute it pieces of real programs. For example, you can take a small loop from a real program and you just use the loop as a small benchmark application to evaluate the performance. More widely used are the real programs. For example, GCC, SPICE, SPEC, suite applications. Those are widely used for evaluating processors' performance. If you read the papers from computer architecture conferences, they use these more realistic benchmark applications. Yeah.
Are these benchmarks for particular applications?
Yes. So there are, for example, spec. It has spec int, spec floating point, also has spec web. So they have different suite of applications for different application domains. For example, spec web, it consists of a number of applications to emulate the programs running on web servers. For example, transaction database, web server. So those are part of the spec web. And spec int, they have integer operations. And spec floating point, then that's a suite of applications with a lot of floating point operations.
Is there any organization which defines this benchmark?
Yeah, so spec, if you go spec.org, that's one organization / commercial entity to release these benchmark tools. There are many other ones out of the research projects from universities. These are often open source benchmark applications that's still being widely used by other groups as a study of the performance. MIPS and MFLOPS, millions instructions per second, and millions of floating point operations per second. Let's first talk about MIPS, millions of instructions per second. The definition is simple. It's measured in terms of the instruction count divided by CPU time. It's equivalent to the clock rate divided by the CPI. It's very easy to understand and easy to market. The problem, a serious problem, is that because different processors have different instructions, so for the same program, you may need a different number of instructions to complete. So even though you have maybe a higher million instructions per second, that does not mean that your program executes faster, because maybe because of this particular instruction set, you inherently have more instructions for the same task. So it is not a very accurate measure to compare performance of different architectures, processors with different instruction sets. For floating point, this millions of floating points per second, it is less compiler dependent because floating point operations are very generic. It's floating point division, it's floating point addition. It's different from the MIPS, whereas MIPS you may have ALU instructions, branch instructions, memory instructions, etc. A lot of variations of these. Not all floating point operations are implemented in hardware on all machines. Not all floating point operations have same latencies. So there are still some issues with just using this floating point operations per second to compare different processors with different architectures, with different instruction set. For the same instruction set, yes, these two are relatively accurate.
But MIPS also support floating point arithmetic.
Oh, this MIPS is not the MIPS processor.
Okay,
It's just the million instructions per second. It's same acronym but different meaning. Okay. Let's stop here.